go for it. Okay, so thank you. I will speak on the block length scaling of polar codes, continuing some other talks in this topic in this workshop. And this is joint work with Dina Goldin. Okay, so let's consider some discrete memoryless channel W with symmetric capacity IW. For simplicity, suppose the W is symmetric, and so IW is equals the capacity. And the goal is to communicate a trait R with error probability upper bounded by some pre-specified threshold P0. And if we are given a capacity achieving family of codes, then for any R less than C, we can find a code with from the family with sufficiently large block length n, such that the error rate will be below the pre-specified threshold. A fundamental question is, how does n scale with respect to the gap between code rate and channel capacity? Without complexity considerations, we know that the scaling is polynomial with respect to the inverse gap between C and R. This is the best possible, and it is also achievable. But what about finite length scaling of computationally efficient capacity achieving codes? This is a different story, much more complicated, and much more complicated question. And actually, the first results only appeared very recently. They appeared after the introduction of polar codes introduced by Arikan in 2009. The computational complexity is O n log n, so they are efficient. And it was shown that the block length scales polynomially. But the question is, what is, now that we know that it's polynomial, it remains to ask what is how small can we set mu? So there were a series of works in on this topic in this short time interval from 2013 and until today. And the best result today is that mu is between 3.55 and 4.7. And similar scaling in N holds also in other problems like lossy source coding and various problems in multi-user information theory. So, okay, so if this is the situation regarding mu, the question is how can we improve or maybe generalize? What else can be done? So one thing that is natural to think about is to apply general polarization kernels or to apply non-binary polar codes. So a recent result that we heard this workshop is that also for QRE polar codes for Q prime, n scales polynomially with respect to n scales polynomially. But in the proof, mu is very large, so can we do better? So in a recent work that we submitted, we show that for Q equal 3, we show numerically that for Q equal 3, much lower values of mu can be obtained. And we think that the technique can be applied to other values of prime Q, but we have not done it yet. Okay, so let's fix notations about polar codes. Block length is n equal 2 to the small n. Generator matrix is Gn. U is the information vector. X is the code word equals UGN. Suppose first that we have a binary DMC, W. So it's from X to Y, and X is 0, 1. The channel output vector is Y, and so this induces a probability distribution. This probability into distribution, And from this, we can define subchannels in the standard way. And what Arikan showed is that typically, either the information of a typical subchannel is very good, so the subchannel is almost perfect, or it is useless. The information is very small. Okay, we encode and decode. We encode the code in the standard way. No point to elaborate on that at this point. Decoding is using the successive cancellation decoder, and we know that for Arikan and Teletar show that for I less than C, the error probability goes to 0 very fast. Okay. Now, in order to analyze the polarization, we use this tree process of channels, which is defined as follows. Suppose that BI are IID random variables, and they are uniformly distributed. They are binary. We start from W, 0, which is at the root. W0 is W, and then we progressively define Wn from 1, 2, 3, and so forth. And now, at each step, Wn minus is formed by check node convolution between W and W, while W plus is formed by variable node convolution between W and W, and this terminology uses standard factor graph notation. For example, you can see it in the book of Richardson and Urbanke. We know that the information of the W minus is the bad channel and W plus is the good channel, and the average information of W minus and W plus is the same as W. So we have this random process. And the relation between this random, it was shown by Arikan, that the relation between this random process and the subchannels that we have in practice is that, for example, if we look at the Bhattacharya parameter of each subchannel, the probability that Zn, our random variable, Zn is Zwn, the probability that it will be in AB is the fraction of subchannels that are inside AB. And similarly for other, for the information, for the symmetric information and so on. And this, Arikan showed that for any fixed small delta, positive delta, we have that we have polarization, which is summarized here. Okay, how do we prove finite length scaling? So for that, one of the possibilities is to use the Bhattacharya parameter. And so if we start with a channel W, producing W plus and W minus as two sons, then we know that ZW plus is equal to Z squared W, while ZW minus satisfies these two inequalities. So if we define some function F0, which is 0 at the boundaries 0, 1, and positive in the interval 0, 1, we define this function in this way. And then it can be shown that the expected value of F0 Zn is exponentially decreasing in little n. This can be used to show, using Markov's inequality, that the probability that Zn has not been polarized, this is also the fraction of channels that have not been polarized, is exponentially small. Now from here the proof goes can go quite fast. After we've shown this, we can say something, say a similar statement about the fraction of channels that has been polarized. And from here we have this relation, which has what is the probability that a channel is information carrying. So it is IW minus some small, exponentially small term. And then following a standard, now standard argument of Arikan, we get the correct scaling result, which is summarized here. So this is how we can proceed with binary codes. Now let's move on to the second part, which is what do we do for QR codes. So instead of Z, it will be more convenient to use the information, the symmetric information. And given a QR input channel W, again, W minus is the check node convolution between two copies of W. And W plus is the variable node convolution between two copies of W. And we would like to obtain this kind of bound for some function epsilon L IW. As motivated by the binary case, we also define fkx recursively in this manner. And the rest of the analysis is very similar to the binary case. If I would like to elaborate, the first step, I can a little bit elaborate on the first step. So like, similarly to the binary case, if we define LKX like this, and LK is the supremum of LKX in the interval 0, 1, then let's look at EFK IN plus 1. We know that IN plus 1 is IN plus with probability half, and IN minus with probability half. So the expected value is this. Now, we also know that IN plus and IN minus, IN plus increases is IN plus epsilon, and IN minus must be IN minus epsilon, because the sum, there is a conservation of sum of informations. So if we take here the supremum, we have an inequality. And now using our definition of fk plus 1, which was set previously, we get this inequality. From here we can, by applying this basic relation, we can repeat it several times and get this inequality. And now dividing by f0 and multiplying back by f0 and using the definition of LK, we immediately get this. Repeating this relation several times, we get that EF0IN is exponentially decreasing, and by Markov's inequality, it can be seen that we can say a statement on the fraction of non-polarizing channels, and the rest is the same as the binary case. So the whole analysis that we propose is very similar to the binary case, except for one difficult problem, which is how to obtain a tight bound. How to obtain a tight bound on epsilon L IW, or how to obtain a good inequality, a good bound on IW between IW and IW minus. How can we obtain a good lower bound? So for the binary case, there are these kind of problems are called extremes of information combining. Sometimes we have a result, but there is no result for q greater than 2. And apparently it is very difficult to find some simple, nice formula. So we went to we suggested a numerical method instead, which I now focus in the rest of my talk. So we follow notation in Karzan and Teletar, which also worked on the QRE channel for lossy source coding. And given a QRE channel WY given X, we define WY in this way. Let's define Vy as this vector, which is actually WY given X normalized. And by this definition, the vector Vy is on the simplex. So it's, the sum is 1 and each element is positive, greater non-negative. It is very simple to show that IW can be expressed like this, or like this, where W hat G is defined here. So this is really immediate. Now consider two channels, WA and WB. The check-node convolution between WA and WB, denoted here is this symbol, is by definition, this is the definition. From this definition, it is immediate to see that to have this, and also to have a relation between expressing VA check-node convolution B. It is simply the cross correlation, circular cross correlation between VB and VA. Now define this function. Under this definition, we have the following. The symmetric capacity of WA check convolution B is equal to this. Why is that so? Because of this. So we just apply it here. And using our definition of G, we get this inequality. Our definition of G is the fact that W is WA times WB, which was said before. We get this inequality. Now, using the definition of WA hat and WB hat, we can write this like this. Okay, now suppose that we are lucky, and G1, G2 is concave separately, not jointly. I just need it to be concave separately in G1 and G2. Then we can say that we have this. IWA check convolution B becomes less equal than G applied to IWA and IWB. If G is not, we are not lucky and it is not concave, maybe you can find an upper bound, we can find a function which is larger than G, which will be, which is concave. Okay. In our case, we take two identical copies. So A is equal B, and W minus is the check-node convolution of W and W, and we have this. Therefore, IW minus IW minus is greater equal to this. And this is our epsilon LIW. Now, one of our main numerical observations was that at least for Q equal 3, a QSC channel provides an excellent approximation to the solution, but it is not completely the solution. It's only an approximation. We need to massage it a little bit in order to obtain a bound. What is a QSC? A QSC, like BSC for the QRE case, is defined by, if the error probability is P, this is the definition. Okay, so first it's not very difficult to prove we can prove some properties of G. Some of them are very easy to prove, like if WA and WB are both QSC, then the WA check-node convolution B is also QSC, and then we have equality of, we can express the symmetric information with inequality. And we have another lemma, which is also this lemma, that when WA and WB are QSC channels, they yield an extreme point in the Lagrangian of the definition of GG1, G2. This is also quite simple to prove. We can also prove some other results. We can show that we don't need equalities here. We can take here these inequalities. This is also very simple to show. And we have this lemma that says that if we actually write this G1, G2 as the 1 minus the minimum value of fu, where fu takes the other variable v, then this fu itself is concave. And actually what this means is that G1, G2 can be computed efficiently using algorithms for concave minimization over a convex region, because if we look at fu, it is defined over a convex, u is defined in a convex region, and fu is concave, so it's minimization of concave in a convex region. There are efficient algorithms for doing it. They provide both upper and lower bounds iteratively. Of course, if we had the other problem like of maximizing convex maximizing concave function in convex domain, this would be better, but this is not the case here. But nevertheless, there are efficient algorithms in this case too, and the number of variables in our problem is not large. It's typical, at least when Q is not too large. We have some other lemmas, which we have some other properties on G. G is monotonically increasing, and it's symmetric. Some of them are also very simple. These lemmas are more complicated, more difficult to show. We can write explicit expressions for G1, G2 for small G1, G2. And for G1, G2 sufficiently close to 1, and Q equal 3, we have this. Actually, it generalizes also for the general case of at least this lemma for a larger Q. Here we need to do some eigenvalue analysis. Here it's some other observation. And so for the extremes, we know an explicit value for these functions, and it matches the value of the GQSC, which I was talking before. Now let's look at some numerical results. So if we look at the contour of the function G1, G2, as I said, it's a function of two variables. We can compute it by the methods that are indicated, using the lemma that one of the lemmas that I indicated above, that fu is concave. We can see that G is indeed monotonically increasing from 0, 0 to 1, 1. It's, of course, symmetric. If we look at the first derivative, for any fixed G2, the derivative with respect to G1 is decreasing, and it's 0 for G1 when G1 approaches 1. And if you look, the most interesting thing is what happens if we look at the second derivative. So we don't need, we only need the function G1, G2 to be concave with respect to with respect to G1 when G2 is fixed, or the other way around, because this is a symmetric function, so it's enough to concentrate on the case where when G2 is fixed, and we look at the second derivative of this function, and so we get these contours. And if we look at this function, it's not, well, we are not completely lucky, because G is not entirely concave, but it is quite close to being concave. And we can make it concave. How can we make it concave? So actually, you have this our function is goes like this, and then it's concave. So I can pass a tangent. Of course, it's exaggerated because it's in most of the region. In most of the region, as we can see here, for most values of G1, it will be concave. Only for very small values of G1, it will not be concave. But we can pass a tangent, and so we can make it. We can obtain a concave upper bound. So this can be done. And actually, we need to do it in both dimensions. So we suggest doing it like here. And in this way, we can obtain a concave upper bound on G. Now, you might be concerned about the fact that this G, we don't have an explicit function for G, but this can also be solved. Actually, we noticed that we can obtain a closed form concave upper bound on this G given by this function. And this is concave function. This can be checked using, for example, Mathematica, something like that. And it is an upper bound on the function that we are on the true G. And so it can be used in the bound. But if you use this solution, we get a slight degradation compared to using G star. So we prefer G. So I will show results both with this and with this. So here this graph shows that GQSC star is indeed concave with respect to G1, and the same for G2. This is perhaps the most interesting thing in the bottom line. Because if you look at the upper bound, at our lower bound between IW and IW minus, you see that this is the blue line is the BSC, is the Q equal to case, where we know from extreme of information combining that BSC yields the bound. For Q equal 3, our numeric approach shows that this is the bound, and it is above the Q equal 2 case, so this is nice. Although the gap is quite small. If you look at suppose that you just take the QSC and look what is the difference between, you assume that the solution is given by the QSC, then you see that there is not much difference between the red line and this QSC. It is a little bit over-optimistic regarding the bound, but it is very close to the real bound that we obtained. And so if we use this bound with G star, the concaved G, then the scaling of n is this, which is much better than was known before. And actually, it can probably be improved when using the newer techniques presented by Mondelli, Hassani, and Urbanke. So it might well be the case that this 6.5 can at least decrease by 1 and perhaps by more, because in the binary case we are using Bhattacharya. Here we are using symmetric information. Perhaps we didn't try too much to. Actually, our work at the first stage concentrated on obtaining better bounds on IW minus, IW minus. We didn't try to improve that too much. In conclusion, we saw that the block length of polar chord scale, it is known that the block length of polar chord scales polynomially with respect to the inverse gap between chord rate and capacity. For binary and now also ternary chords, this polynomial has low degree. probably the technique can be extended to larger queues. One main issue is to consider is the question whether the scaling actually decreases with respect to Q. This is an open problem which should be considered in the future. Okay, thank you.
I think we have a requirement that anybody mentioned in the talk has to ask a question or make a comment.
This is the last talk. So.
Yeah, you've got to ask something.
I have a quick question. So the polar code you're assuming is the 1-1-1 matrix? I guess there's one other choice you could do, like 1-1-2 or 1.
Yes, this is the standard polarization. It's the standard polarization kernel, but with QRN, not binary. Of course, it is. It only polarizes for prime Q. There are examples where you can show that polarization might not occur when Q is not prime. One interesting possibility, perhaps these type of bounds can be used also with generalized kernels. This is one possibility.
Is there any reason to believe this will be monotonic in Q? Is it well understood?
I really don't know. This is what is the dependency with respect to Q. I mean, if it is really, I don't know even if it. I don't know if it will be. I'm not talking about. Forget about the scaling. Let's just look at this bound IW minus IW minus. The question is whether it improves with Q. I don't know if it's true or not. This is not known. And again, this is really, you see that we could not come up with something nice like in the binary case. We had to do some numerical work to bypass this problem.
Great. Thank you very much.
Thank you.